Yes, welcome to the second lecture of this last series on image processing applications of linear algebra in image processing. So I hand over this session to Dr. Gaurav Bhatnagar.
Okay, thank you, Dilpreet. Am I audible and my screen visible to all?
Yes, you are audible. Your slides are also visible.
Okay. So before I start today's lecture, let me have a quick question around if students might have in their mind whatever we have done in the last lecture. So if there are some queries and if you want to ask, I think we can take 5 minutes and then try to clarify those. So Dilpreet ji, if there are some questions in the chat box, please let me know. Okay, so it seems that no query are there from the student side. So let me start the second lecture of this particular series where we are going to discuss the applications of linear algebra, specifically in the image processing. So before we are going ahead, this slide will summarize the recap which we have done in the last lecture. So we started the last lecture with the definition of the linear algebra, where we have given the definition of the linear algebra and what is the meaning of this word linear algebra. Then we have seen a very quick connections of linear algebra in different areas like finite geometry and the system of equations. Then we started the actual agenda of this series when we try to explore the connections of linear algebra and image processing. Then we have seen in the last lecture that why a digital image is always going to be a matrix and what is the mathematical reasoning behind it. Then we have seen how uh, how color image look like mathematically when we try to have a color image. Then we have seen the connections of linear algebra with the colors which we are going to have around us and how these colors will reflect in an image. So in today's lecture, we are going to discuss about uh, one very versatile tool of linear algebra that is called the singular value decomposition, which is and this tool, singular value decomposition, is not only very famous in mathematical community but also in the engineering community due to its wide applicability in the applications in the diverse applications. So today we are going to discuss and try to witness the importance of singular value decomposition mathematically as well as from the applications point of view as well. So let us start the journey of today's lecture, towards the goal to explore the singular value decomposition. Okay, so while singular value decomposition is very famous in mathematical community and application-oriented disciplines, so when we try to explore the linear algebra, then there are few shortcomings of linear algebra or the techniques which we are going to have in linear algebra. So the first and the major drawback which we usually face is the with respect to the invertible matrices. So a lot of techniques and tools or processes are going to be there for the square matrices as well. As soon as we are going to have we are going to have a rectangular matrix, things actually changes, and then we are going to have very limited tools in our hand. For example, let me talk about the inverse of a matrix. So when we talk about the inverse of a matrix, the underlying assumption says that given matrix is going to be a square matrix. Because we can always find our determinant of a square matrix only, and if we are going to have a determinant of a matrix, then we are able to identify whether it is singular, non-singular, and we know that for every non-singular matrix there exists the inverse. So whenever the invertibility comes for a given matrix, the general perception says that my underlying matrix is going to be square. But what will happen if I'm going to have a rectangular matrix? Because in the real life problems, when you try to model any problem through the linear algebra, you no longer going to get a square matrix. It is going to be very hard to digest this fact that most of the real phenomena will lead to a rectangular matrix rather than a square matrix. And then we are going to have a very limited tools with respect to the rectangular matrices. Hence, whatever we are learning in linear algebra with respect to these square matrices is not sufficient to provide the complete sight of that particular real phenomena. So we are looking for something which is applicable for the rectangular matrices as well, and it is going to be as robust as possible, as we are going to have something for the square matrices. Like another example at this point of time, which I want to take, the eigen decomposition of a matrix. Of any matrix. So eigen decomposition, I'm meaning about the spectral decomposition of a matrix. So there are different names for this term eigen decomposition. Some books says eigen decomposition, some books say spectral decomposition. But the underlying idea is you are able to, if you are able to identify the eigenvalues and eigenvectors of a matrix, then you can always write a particular matrix as let's say Q transpose. This is going to be a diagonal matrix including all the eigenvalues of this matrix A, and this is going to be one of the matrix which actually have the eigenvectors with respect to all the eigenvalues in the columns in its column. So this is nothing but the very simple example of eigen decomposition or the spectral decomposition. But in this case as well, when we talk about the eigenvalues and eigenvectors, and these eigenvalues and eigenvectors are going to have a very vast application in the different domains. However, everything boils down to the square nature of the matrix. As long as the matrix is square, I can always identify the eigenvalues and I can always identify the eigenvectors. That's a different story whether all the eigenvalues are distinct or not, whether it is diagonalizable or not. But those are the different questions which can be answered very easily. But whenever we talk about the eigenvalues, finding the eigenvalues and corresponding eigenvectors, the matrix has to have a square in nature. If A is not a square matrix, then we are not able to identify you can say the eigenvalues of it. Now, if you try to just observe the relationship between this linear algebra and image processing, I know that image processing, every image is going to be a matrix, and whenever you try to take a photograph from your camera or mobile, you are not going to have a square image. You are going to have a rectangular photograph. So the meaning is we are more interested in those tools which will help us to process the rectangular images rather than the square images, because the square images we are going to have sufficient number of tools. So this is a singular value decomposition is one such tool which can handle the square cases as well as the rectangular cases. The other thing is eigen decomposition is not unique. Everyone knows that this eigen decomposition which we are going to have is not unique in the sense that given a particular eigenvalue lambda, you are going to have the multiple eigenvalues. Let's say eigenvector. If V is going to be the eigenvector, then any multiple of V is also going to be the eigenvector of matrix A with respect to the eigenvalue lambda. Hence, this V is not unique, so Q is not going to be unique. But now we are looking for something which will try to give us something unique even for the rectangular images. So, and then we are more interested in the invertible matrices, then unique decompositions. Then these are the two applications or the two scenarios which comes from the mathematics point of view. But from the image processing point of view, we are going to have two other things called the noise removal and the data compression. So as this lecture will progress, we will about to see these particular applications as well. And the ultimate goal of this lecture series is to culminate the whole process with a very decent or the widely used technique called the principal component analysis, which is actually based upon the singular value decomposition. And it will help us to reduce the dimensionality of the data. So if you look at it, for the simplest example, I think you have some lecture in the Facebook or Google. So if I consider the Facebook, and if I just want to know the data which is stored in the Facebook server, now you can see the millions of users are there, billions of users are there, and those billions of users are going to have different connection with different peoples. So if I want to summarize all those things uh, in a form of data, then that data is going to be huge. And that is going to be the curse of actually the curse of the data science, where the curse says the data is going to be highly dimensional. So I'm going to have the different dimensions to the data, and these dimensions are going to create a lot of problem for me because in order to process huge data, I should have a very good computing facility. If I don't have a good computing facility, I cannot bring out a meaningful information out of that particular data. So I cannot even, in other words, I cannot process that data with an ease. So I'm looking for some technique just to take care of these things that which can reduce the dimension of data without the information loss. So I don't want to I don't want to lose the information. However, I just want that data has to be compact in as small in a small component as small as possible so that the regular computing facility can process that particular data. And this PC is going to be one such technique which will try to reduce the dimensionality of the data for the further processing. And this principal component analysis is purely based on, there are different ways, actually different ways to implement the principal component analysis, but the most efficient way comes from the form of the singular value decomposition. So maybe in the next lecture, we are about to discuss about the principal component analysis and how the things will move from SVT to principal component analysis. So this is the whole agenda of today's lecture and a gist of the discussion which we are going to do in the next lecture in this particular lecture series. So now let us start with this versatile tool called the singular value decomposition in the linear algebra. And then we will see that how things will go or how things will move with this particular singular value decomposition. So in order to give you a brief motivation why and how this particular point which I have mentioned, data compression, is actually required, or how this high dimensionality is going to be a curse, let me give you a very simple example. Let me consider these two matrices A, or let me say for the simplicity, let me say this is going to be a matrix B. So I am going to take the two different matrices. The size of this matrix is again going to be the 6 by 6. This is again going to be 6 by 6. Now I want to store these matrices in the computer. I know that I can always save all this data because when I collect data, I need some resource to store that data. And in order to store the data, that the computer is going to be the hard drive or maybe CD or maybe pen drive, whatever medium I have is going to be quite useful. So I just want to store this data. The meaning is when I try to store this 6 by 6 matrix, essentially I'm trying to store the 36 numerical values. In this case, this is going to be the integer, so I can say that I just want to store the 32 integers into my storing device. Now the question is the space required to store this particular 36 integers is going to be little high. Is it possible that I want to store the same matrix in a very less amount of storage capacity when compared to the 36 integers? So is there any way? So can anyone tell me, is there any way how to store the same matrix without storing the 36 values? I just want to store maybe 10 values, 8 values, 5 values, maybe 6 values. Can anyone tell me how to proceed? Any intuitive idea? So whosoever is want to reply, please unmute yourself and you can reply or respond to my query. So I don't want the objective is I don't want to store the 36 values. I just want to store the some number of values which are far less than this 36. And this concept is called the compression. When you just try to find a redundancy in your data and then remove those redundancy and whatever the essential components are, you are going to store those particular data. So anyone? Okay, so let me tell you very simplest solution. So if you store some of rows. Okay, so Devanshu is asking, saying that we need to store the sum of rows. But the storing the sum of rows will not suffice the requirement. Here the case is very simple. Now can you apply that the same concept in the second matrix when the numbers are different? Here the number is same, so you can certainly do that. But in general, that is not going to be a viable option because it may possible that all the elements in a row are going to be distinct. And when that is the case, then summation is going to be very highly ill-posed problem when you are going to have the 6 variable and one given information. So using this one sum, you cannot uniquely identify these 6 values. So the meaning is if you are taking the summation of the row, you are going to lose the information that at one place what percentage of this sum will go, at the second place what percentage of this sum will go, and so forth. So of course, for this case, yes, I can say your option is viable for at least for this matrix only because all the values are same. But in the easiest solution is the factorization. If I am able to factorize this matrix into the tiny matrices such that after having the matrix arithmetic on those tiny matrices, I can always construct this bigger matrix A, then I am able to restore my big matrix in a very small manner, and the requirement is going to be very less. So now let us see what will happen in this particular case. So I can write this matrix as the multiplication of two vectors. So this is going to be a column vector, this is going to be a row vector. Let's say this is going to be some vector C and this is going to be some vector R. So whenever I multiply C with R, I am going to get the same matrix A which is given to me. And in order to store this matrix A, what I am looking at, I am looking at the storage capacity to store 36 integer. However, in this case, I am just looking at the storage capacity for the 12 integers only, and then some space for storing that I am looking, or the operation is going to be the multiplication of these two matrices. So if you are going to follow a uniform policy that okay, all the factorization is going to be multiplication, of course all the factorization is going to be multiplication. So this particular value or this particular information is again going to be redundant in nature, and essentially you are going to have the 12 integers storage capacity requirement to store this particular matrix A. So I'm going to store C and R, and whenever I want to retrieve my matrix A, I just multiply C with R, and I'm done. So the factorization technique which we are going to have in linear algebra plays a very vital role to optimize the storage capacity for different data volumes which we are going to have with us. Now, let us try to have a similar example in this particular matrix B as well. So now this is going to be a matrix and I just want to store this matrix. So now since the dimension is 6 by 6, so again I'm looking for the storage capacity over 36 symbols. Again, I cannot take integer because these are not integer. I don't know what kind of value is this. So I'm assuming that these are the characters. So I'm just saying that I'm looking for the storage requirement for 36 symbols. So now, again, the motivation and objective is going to be same. The objective says instead of Dilpreet, my voice is not clear.
No, it is good for me.
Okay,
Voice.
because I guess there was someone is there who wrote that voice is not clear.
Probably the is from
Okay,
their side.
okay. I think you can maybe check the speaker or something. I don't know. Okay. Okay, so there are few comments as well. So they are saying clear. So I think there is no problem, at least from my side. Okay, so now we are coming back to this example. Again, the objective is to store this particular matrix, but not in the storage capacity of 36 symbols. I just want to reduce it. So again, the motivation says that if I somehow I'm going to factorize this matrix in some tiny matrices such that after multiplication of those tiny matrices, I'm going to get this matrix back. Then I am done and I'm going to store this matrix in that particular manner. So let me see that particular kind of factorization. So again, as I rename this matrix as A as B. So let me take this B. So now if you quickly look at the pattern over here, so this row is actually repeating in this particular matrix. So this matrix can be factorized in these two vectors. One is the column vector, the one is going to be the row vector, such that the multiplication of these two is going to give you the matrix B. And again, the storage capacity for these two vectors are again going to be the 12 symbol. It's nothing but the requirement just to store the 12 symbol instead of 36 symbol. So when you have this kind of phenomena, when you want to store the complete information in less in a very less capacity, then this concept is called the data compression. And now data can be of anything. Data can be the textual data, numerical data, or you can say the audio data, video data, image textual, or you can say the visual data, the like images. So now the nature of data is going to complicate the process or maybe give you the very easy process. But the data compression means that you just want to reduce the storing capacity of a given data. And the data can be of any type. So that is going to be there. So this is a very brief motivation why the factorization techniques are actually very famous when you talk about this signal processing, when you talk about image processing, or maybe you can talk about the video processing, or in general, the data processing, where you are going to have the huge volume of data and you are going to do that. But the only problem is this factorization unique or not? If it is not unique, then you might face some problem for certain kind of matrix. When the matrix is nice and clean, then you can certainly go ahead with the factorization technique. But when it is not unique, then there are few matrices which will give you some trouble, and then you are going to use your wisdom to tackle those situations. But the factorization techniques are the best tool for the compression. So now, motivating by this particular factor, we are going to have a lot of factorization technique. Let me name some of them right now in front of you. The one is the LU decomposition method. Then you are going to QR decomposition method. Then we are going to have the spectral decomposition or the eigenvalue decomposition, and many more. These are going to be the some of the factorization technique. So there are going to be some loophole in each and every technique. So the biggest loophole which I can observe right now is most of the decomposition or the factorization technique will are only for the trying for the square matrices, or if they are working for the rectangular matrix, then they are not going to be unique. So in order to overcome these things or these shortcomings or loopholes, we are going to have the one solution that is called the singular value decomposition. And that is why the singular value decomposition is going to have the diverse applications in diverse domains, and is going to be very unending story for singular value decomposition. You can go in any discipline, in any domain, you will definitely going to find the application of singular value decomposition. The only thing is you need to understand how the singular value decomposition is going to be applicable in that particular domain. So now let us let me define the singular value decomposition for a given matrix A. So as I mentioned, that SVD is one of the most powerful tool in linear algebra, and is going to be factorization and approximation technique. So the SVD is not going to work as a factorization method, but also as the approximation method, which effectively reduce any real or complex matrix into smaller and invertible matrices. So now these two words are very useful in terms of in terms of single value decomposition. So when you go back and try to have these factorization technique, so they are going to give some matrices to you. It may possible that some of these matrices is going to be specific property, but not all. Like for QR decomposition, I know that Q is going to be the orthogonal matrix, and R is going to be the triangular matrix. That is going to be the philosophy behind the QR. But none of the thing is going to be ensured that all the matrices are going to be are going to be invertible and all the time. For regardless of the input, you are going to get that. So it may also possible that there are going to be some example where the QR factorization actually doesn't exist. So what will happen in those cases? So we are looking for a versatile tool which will definitely going to give me a factorization where a matrix which may be a real or complex has to be factored into the smaller matrices, and all those matrices, whatever factor we are going to get, are going to be the invertible. So all these smaller matrices are going to be the invertible matrix, and this particular deadly combination will make SVD is a prominent tool in the diverse disciplines. So mathematically, if I look at the definition of singular value decomposition, so this decomposition is nothing but any matrix A can be decomposed into the three different matrices U, sigma, and V, where this is going to be a diagonal matrix, and these two are going to be the orthogonal matrix. Orthogonal matrices. Whenever you have such kind of factorization, then this factorization is called the singular value decomposition. Now, A may or may not be a square matrix. So this definition is very generic, and it is going to have the implications on the sizes of these particular matrices. So for the square matrices, R are going to be the square matrices. When we are going to a rectangular matrix, then not all are going to be square matrix. Some is going to be square, some is going to be rectangular, and that is how we are going to have the classification of the singular value decomposition. So this particular definition is the matrix definition of singular value decomposition, and this particular slide is going to give the vector definition or the vector representation of SVD. So now let us have a very quick discussion of the sizes of this U, sigma, and V, and what are the meaning of this particular value. So as I mentioned that for any matrix A, I am going to get a three matrix U, sigma, and V. And of course, when I have the V, I will get the V transpose. So this U is called the left singular vector. Singular vector of matrix A. So this U is going to be a left singular vector because it is going to be operated on the left side, leftmost side. So that is why it is going to be left singular vector. This sigma is again going to be the singular or the matrix of singular values. Singular values of A. On the other hand, this V is going to be the right singular vector. Right singular vector of A. So now let us see the composition of the U, sigma, and V. This is going to be a diagonal matrix. This is going to be diagonal matrix where all the singular values of matrix A are listed in the leading diagonal in the decreasing fashion. So the meaning is the first singular vector, if I say this is going to be sigma 1, this is going to be sigma 2, then sigma 3 up to sigma n, then these all sigmas are going to follow the certain rule which say that sigma 1 is always greater than equal to sigma 2, is always greater than sigma 3, is always greater than equal to sigma 4, and so on up to sigma n. So the first first singular value of the matrix A is going to have the maximum value, and as you go further, you are going this value is going to be reduced, and the value of sigma 2 is always less than equal to sigma 1, and so on. So this is going to be the one of the property which the singular this diagonal matrix or the matrix of the singular values is going to be have. Now U and V are two special matrices which are going to be orthogonal in nature. So U is again going to be orthogonal matrix. So it is orthogonal matrix whenever the A is real. Of course, whenever A is real, then it's going to be orthogonal. And whenever A is complex, then what is the respective counterpart in the real domain? Oh, sorry, complex domain. So what is the actual counterpart of orthogonal matrix in the complex domain? Anyone? I hope that you know about the orthogonal matrix. So a matrix is called orthogonal when it follows the same thing. The relation U transpose is equal to I is equal to U transpose U. I hope you know this definition of the orthogonal matrix. So if this is the definition of the orthogonal matrix, and orthogonal matrix is going to be real matrix, then what will happen if the matrix is going to be complex? So in that case, instead of taking just the complex this transpose, we have to take the conjugate as well, and that kind of matrix is called the unitary matrix. Yes, exactly. So the Vanshu has given the right answer. That's going to be unitary matrix. So this U is going to be the orthogonal matrix if A is real, and is going to be the unitary matrix if A is complex. Again, for unitary matrix, I am going to have the relation of U theta is equal to I is equal to U theta U. So there theta is nothing but the conjugate transpose of the matrix U. Okay, so now I will not go in a very complex manner since the images are going to be the real matrices. So let us work with the orthogonal matrix. However, this can be extended very easily for the complex domain as well. So now what is so beautiful about this particular relation, whatever you are going to have? So this particular relation will ensure that your matrix is going to be invertible. Because if you take this particular relation U transpose is equal to I, this essentially says that U inverse is nothing but U transpose. So whenever you are going to have an orthogonal matrix with U, then that matrix is always going to be the invertible, and hence the part which I mentioned in the previous slide, that it is going to have the factorization, the small matrices which are invertible. So due to this orthogonality of this particular matrix, the inverse of this U is always going to exist, and hence U is always going to be invertible. And the inverse or finding inverse is very easy. You just take the transpose of U, you will get the inverse. So you no need to do the long calculation of finding out the adjoints, and then you have to solve the whole process and then try to find out inverse. Or you can even apply this Gaussian elimination or Jacobi method to find out the inverse. So no need to go for those particular mechanisms. You just take the transpose, you are done. You have the inverse of U. The same observation can be given for the matrix V. V is again going to be the orthogonal matrix whenever A is real, and it is going to be unitary matrix whenever A is complex. And again, since it is an orthogonal matrix, then of course it is again going to follow the relation V transpose is equal to I is equal to V transpose V, and this will essentially says that V inverse is going to be V transpose. So the matrix U and V are going to be invertible as well as orthogonal, and the sigma is going to be a diagonal matrix having all the eigen or the singular values on the leading diagonal. So now let us try to understand what will happen with the sizes of this particular matrices when A is going to be a square matrix or A is going to be a rectangular matrix. So now let me pictorially represent the singular value decomposition and what is going to happen with this particular scenario. So let's say the dimension of A is going to be n cross D. Then this factorization is going to give me a matrix U, which is going to have the size of n cross n, sigma, which is going to have a size of n cross D, and a matrix V, which is going to have a size of D cross D. So now you can now look at uh, since these are the factorization of this matrix A, then the multiplication of these three components will give you your matrix A back. Then you have to ensure that the dimension of U sigma and V are such that the matrix multiplication is going to be ensured. So in this particular case, the multiplication is going to be ensured. How, what is the problem now? The problem says is, I mentioned in the previous slide, the sigma is going to be a diagonal matrix. However, diagonal matrices are always going to be square. That's what we know about the mathematics, that all the diagonal matrices are going to be square matrices. But here what I'm getting n cross d matrix. So these kind of matrix where at some point or at some location you are going to have a diagonal matrix, and after that you are going to have some zeros, then those kind of matrices are called the rectangular diagonal matrix. So this sigma is actually a rectangular diagonal matrix. Rectangular diagonal matrix. The meaning of rectangular diagonal matrix is you are going to have a matrix, and up to a certain time, let's say R, you are going to have perfect diagonal matrix. All these elements are zero, all these elements are zero, and after this R, this is going to be all elements as zero. And this R is nothing but the rank of a matrix. Rank of matrix A. So whatever the rank is there for this matrix A, that up to that particular part R, I am going to have a perfect diagonal matrix, and after that rest of the elements are going to be zero. So let me assume the rank of A, or the rank of A is going to be R. Then in this rectangular diagonal matrix up to R in both the directions, I am going to have a perfect diagonal matrix, and rest of the elements are going to be zero. So these are all 0, 0, 0, and 0. Similarly, since I have taken the rank R, then the similar kind of things I am going to have in the U and V as well. So in the U, again, I am going to take always a component, because whenever I say R cross R, so I can always delete these zeros, then this will become R cross R. In order to make the compatibility with respect to multiplication, this is now going to become N cross R. So the meaning is, after the rank R, whatever rows or vectors I am going to have that are not that much important for this particular matrix, and we can certainly remove those vectors to further reduce our matrices. So, or to make our matrix smaller in nature. Similarly, if I want to take again this multiplication compatible, then this matrix is going to be R cross D, and hence my V matrix is going to be D cross R. So so the meaning is, after this, whatever I am going to have over here, all the vectors or all the rows, I can delete that to get a very small matrix into the picture. So now these two scenarios will give you two type of similar value decomposition. So first set of sizes is where you are going to get the maximum size of all the factors, because this is the maximum size I can have in this factorization for U. This is the maximum size I am going to have for the sigma, and this is going to be the maximum size for the V. So the meaning is, whenever you are going in this direction, when your U and V are square matrices of different size, of course, and sigma is going to be a rectangular diagonal matrix, that SVD is called the full SVD. Full singular value decomposition. So this particular word suffice that the dimension of my factored images or factored matrices are of maximum size. I cannot go beyond the size which I am going to have in the full SVD. However, when you have this full SVD kind of scenario, again you are increasing the computing power or the storage capacity for the factorizations or what is matrix, because I know that in this particular matrix, almost all the elements are going to be zero. So no need to store all the zeros element. It may also possible that instead of storing this big matrix, I will just store a vector having all the non-zero singular values over here. So then the scientists think, or mathematicians here thought of, okay, the whole purpose of the factorization is to reduce the computing load as well as the storage requirement. But that these two purposes are not served by this particular factorization. So full SVD is going to have very limited uh, usage in diverse applications. However, if you go in the second direction, when you are going to say that, okay, I am okay if my U and V are rectangular in nature, but I want my sigma as a perfect diagonal matrix, then you are going to get the reduced SVD. Then you will get the reduced SVD. And this reduced SVD is going to have numerous application in diverse application, because this reduced SVD is going to serve both the purpose. The first thing is you are going to have the less computational load, and plus you are going to have the less storage capacity. Of course, we can further exploit the pattern or the structure of U and V into the taking into the account for further reducing the this storage requirement of this particular matrix, that we can do. But right now I am not getting into it because there's going to be a very far different direction or the orientation for the singularity function. Right now I am going to stick myself with the full SVD and the reduced SVD. So using these dimensions of these particular factored matrix, I am going to have the full SVD or the reduced SVD. So reduced SVD will exploit one more property of matrix, that is called the rank. So R is nothing but going to be rank of A. So this particular thing will again give you a very nice relationship between the linear algebra and this singular value decomposition. It says that if you have the singular value decomposition of a matrix, you no need to find out the rank. You just look at what are the non-zeros eigenvalues of or the singular values of this matrix A, which are listed in this matrix, and that is nothing but the rank of your matrix. So SVD will give you a very nice formula for the rank. So rank of any matrix is nothing but the number of non-zeros singular value. So this is again going to give you a very nice way to find out the rank of a particular matrix. So this is how this singular value decomposition is not only very valuable for the mathematical community, but also for the different disciplines where it is going to find diverse application. So now let us continue the further discussion how to actually identify this factorization. Because it is very easy to say, okay, you have to find out three different matrices, U, sigma, and V, such that U and V are orthogonal, sigma is going to be diagonal matrix. But actually, how to identify these particular matrices? So now let us try to understand what is the algorithm, what is the process by which we can observe the singular value decomposition. Okay. So, but before getting into it, let me give you a very simple geometric interpretation what is actually happening with this factorization. So, I know that if A is going to be a matrix, it has to be factored in U as V transpose. Fair enough. So, this is going to, so I will assume that the singular value decomposition exists for this A, and I am done with to represent it geometrically. Now, whenever you try to represent any factorization method geometrically, you are just looking for the system AX is equal to B. Given a matrix A, and if you multiply this matrix by another vector X, then it is going to modify this into another vector Y. Then how this X is changing into another vector Y will actually give you the geometrical representation of any of the factorization technique. Okay, so let us continue our discussion. So the deviation of X from Y will essentially give the geometrical interpretation for any of the matrix. So this is the underlying phenomena when you try to find out the geometrical interpretation of any of the factorization technique. So now what is happening with this single value decomposition? U and V are orthogonal in nature, as I mentioned in the previous slide. So now can you give me one orthogonal matrix which you are going to use a lot of times? Any matrix which you have used a lot of times? Any orthogonal matrix? Please do not give me the identity matrix. I'm not actually interested in that. Any matrix, maybe the of size 2 by 2, of size 4 by whatever its size may be. Which orthogonal matrix you are actually using right away from your 11th class when the geometry introduced to you? I think in the last lecture we have seen that matrix. So anyone is going to give the wild guess to it?
Sir, it's cos theta, sin theta, minus sin theta, cos theta.
Okay, what is the name of that matrix? Rotation matrix. Yes.
Rotation matrix. Hmm.
Yeah, rotation matrix. So this is the simplest example of orthogonal matrix which you are using right away from your 11th standard. And this rotation matrix is not leaving you at all. Wherever you go, if the geometry is there, the rotation matrix will come. So what is going to be the main property of this? It actually uses to rotate things, maybe vectors, maybe shapes, maybe objects, whatever it may be. But rotation is going to give you the rotation of the axis. So now, when I say the U and V, these are the orthogonal matrices. So these are going to be the some kind of rotation matrix. So the effect of U and V in this particular transformation from Ax to Y is nothing but rotation. So now let me take this any two unit vectors. So this v1 and v2 are the two general unit vectors. Then if I'm just going to take it is nothing but Ax is equal to U S V transpose X. So now I'm just following this particular path. Let me take this because this is a matrix. This is a vector. You are going to get some other vector. So if I take any vector v2 and apply over here in place of x, then the output of v transpose v2 is nothing but a rotated version of it. So let me take after the rotation, I am going to get this e2. So this particular multiplication of v transpose with any vector is going to be a rotation. Is going to be a rotation. Similarly, if I take another vector v1 and then just plug in this vector v1 in the place of x, then the v transpose v1 is going to be a rotated version of that is going to be e2. So whatever the angle is going to be there in between these two vectors, the same angle you are going to get over here after the rotation. So the multiplication of v transpose is going to have a rotation. So let me say this is going to be some x1. So now I am looking at S multiplied with S1. S is again going to be matrix. S1 is going to be vector. So you are going to get another vector, let's say X2. Now what will happen with this X2? So S is going to be a simple diagonal matrix where you are going to have all the elements in diagonal, but you don't have anything outside. So now if you go back to geometry and when you try to have the scaling of vector or scaling of objects, what is there? The scaling is nothing but done by the matrix Sx, Sy, where all elements are in a two-dimensional space. So this is nothing but the scaling with respect to x direction, scaling with respect to y direction. So whenever you are going to have a diagonal matrix will always lead to the scaling. So whenever you have these two vector e1 and when this new vector e2 is multiplied with sigma, then with the corresponding value of sigma, it is going to be stretched or the scaled. So let's say it is going to be scaled in this particular manner. Now you are going to have this new vector with you. In the similar manner, you are going to have another sigma value, sigma 1 is going to be in this particular manner. Now, if you recall the previous discussion, it says that all the entries in S are in decreasing fashion. So जो सबसे पहला singular value होगा, that will lead to the maximum displacement or maximum scaling. And as long as you are going with the nth singular value, that scaling is going to be reduced and reduced. And then at the end of the time, you are going to get the same vector which you are going to have before the application of sigma. So that is why this unit circle is somehow become a ellipse. So this particular domain of circle is now converted into a ellipse, and this is nothing but the scaling effect which is going to be there due to this sigma. So this is nothing but scaling. Now if you take this vector again, because now you are going to, this is nothing but my x2, and if I apply this x2 on u, I will get another vector, and that is going to be my ultimate goal to achieve this y. And then again, what you will do this is u is going to be a orthogonal matrix, then there is going to be a rotation into the picture. So this is now going to be rotated either in this way or that way. So without loss of generality, since we have the abstract things with me, I am saying that the rotation is in the positive direction. So I'm going to take this particular rotation. So this new position of sigma 2 E2 is going to be this particular value after the multiplying with the vector U or this matrix U. So this again going to be rotation. So the SVD is nothing but the combination of two rotations and one scale. So this is nothing but the theoretical interpretation of the singular value decomposition. So whenever you try to form a new vector y from this x with respect to matrix A and singular value decomposition, then everything is going to follow a regular path of rotation plus scaling plus rotation. So these are the very basic operations which we are having from our early days of mathematical education, and these particular operations are going to give us a new versatile tool called the singular value decomposition. So the effect of singular value decomposition is always going to be the rotation, scaling, and rotation. And what is the angle of rotation here? What is the measure of what you say scaling in this particular part, and what is the angle of rotation over here is purely going to be decided by the matrices V transpose sigma and U transpose. So the rotation can be in any direction, and the scaling is also going to be with any magnitude. But again, the singular values are responsible for the scaling, and singular vectors are responsible for the rotation. So this is a very simple, what you say, the interpretation of the singular value decomposition, geometrical interpretation of singular value decomposition. So let me take 5 minutes now. Do you have any queries so far? So otherwise we will proceed further and see the algorithm to find out the singular value decomposition. So anyone, any question or any query?
Sir, what is the rate part in this in the EU matrix in your previous slide?
What is the
Rate part in the, you showed in the sigma matrix, that is a R cross R square matrix. Yes. What is the rate part in this EU matrix in cross R?
you are talking about this blue region, basically.
Yes, yes.
This
Is
region.
it whole zero?
No, it's not zero. It's non-zero entries. But these are the non-zero entries created by zeros of sigma. So whenever you multiply this with zeros, essentially you are going to get output as zero. So these are the redundancies which we are going to have in U.
Okay.
Try to understand, when you multiply these things over here, what will happen? And the essence or essential contribution of the multiplication of these components with these zeros over here in this blue region, ultimately is nothing but the adding zeros in the non-zero values in the multiplication. So the value is essentially not going to change. That is why we can remove this. But these are not zeros. These are the non-zeros entries. Maybe positive, maybe negative, whatever it may be. Okay.
Okay.
But when you multiply these three matrices, the essential effect or the final effect is going to be nullified.
Yes.
Okay. So any other query, or let me proceed further with the algorithm of finding SVD. It seems there is no worry, so let me proceed. Okay, so now let us have an idea, intuitive idea how this signal value decomposition is going to be obtained. And then there's going to be a very nice theory of it, and let me try to explain that to you. So algorithm to find actually, I think I have missed one. Anyways, once a matrix A is given to you, what will happen? As long as a matrix A is given to you, when is going to be a square matrix, is going to be a rectangle, doesn't matter. You are going to have two information in your hand, A and A transpose. Okay, given A, you can always find out A transpose. So the meaning is, if I give you A, essentially I'm giving you two information, A and A transpose. So let me take very simple example of a matrix A of size n cross D, and in that particular case, I am going to have a matrix n cross D and I'm going to matrix A transpose D cross N. Now, if you clearly look at these two matrices, these are compatible with respect to matrix multiplication. So I can multiply A with A transpose and A transpose with A. So given A, I am having the two matrices A and A transpose, then essentially I can always find out two matrices A transpose and A transpose A. The size of the matrix A transpose is going to be n cross n, and the size of this matrix is going to be D cross D. So doesn't matter whether your A is a square matrix or a rectangular matrix, the matrix A transpose and A transpose A are going to be square matrices. Other thing, for the moment, let me say my D is equal to N. So I'm just talking about the square matrix. Whenever I'm going to a square matrix, then again I am going to have two square matrices, but now of the same size. The underlying idea says, regardless of the nature of A, I am going to have two different square matrices, and now I can do anything with on these two matrices, which I can do for any other matrix. So now let us go ahead with the A transpose. So A transpose is going to be a square matrix, and whenever you take the A transpose, the beauty of this matrix is always going to be symmetric matrix. So now let me take a very simple example. Let's say my matrix A is going to be 1 and 2. So and then A transpose is what? A column vector 1, 2. Now let me take A transpose is going to be 1, 2 multiplied by 1, 2. So what you will get? You will get a 1 cross 1 element over here because the size is 1 cross 2 and 2 cross 1, and a matrix of dimension 1 is always going to be symmetric. No issues in that. So now let me try to take the A transpose. So you can find out this value. I'm not getting into the multiplication of that. Whenever I take A transpose A, I am going to get 1, 2 and 1, 2. So this is going to be 2 cross 1. This is 1 cross 2. The output is going to be 2 cross 2. So can anyone quickly give me the values? I think this is going to be a matrix.
Right.
So now you can see what kind of matrix is this. This is always going to be the symmetric matrix. So doesn't matter what kind of matrix is a real matrix, is a complex matrix, is a square matrix, is a rectangular matrix. But when you try to find out A transpose A or A transpose, then depending on this N and D, you are going to get a symmetric matrix. And symmetric matrix is always going to be a square matrix. And one of the major main property which we are going to have for symmetric matrix is all the eigenvalues are going to be. क्या होता है property symmetric values के eigenvalues का? Are going to be real in nature.
Yeah.
If I impose another condition that is going to be positive definite, then that is going eigenvalues are going to be positive. So that's a again different thing. But right now, this A transpose and A transpose A are going to be the symmetric matrices or square matrices. So I can immediately identify the eigenvalue decomposition. So yes, or the spectral decomposition to it. So this can be written as let's say Q, and now I'm going to take this as the, let's say, uh, lambda, not lambda. Let me take the matrix sigma 1 and Q transpose. So this is nothing but the collection of all the eigenvalues of A transpose, and these are nothing but the collection of the corresponding eigenvectors. In the similar manner, when you take A transpose A, again you are going to have some decomposition for it. Eigen decomposition for it, because it's going to be symmetric matrix, and again I'm going to have let's say R sigma 2 R transpose. So now these matrices which we are going to have is going to give me the singular value decomposition. Can anyone tell me what is the relationship between the sigma 1 and, sorry, this gamma 1 and gamma 2? So what about the eigenvalues of A transpose A transpose A? So the eigenvalues of these two matrices are going to be same. So let me have a very quick proof for this. The eigenvalues of A transpose and A transpose A is going to be same. So let me say that lambda V be a eigenpair of A transpose. So the meaning, if this is the eigenpair, then by the definition of eigenvalues and eigenvectors, I can always say that A transpose V is nothing but lambda V. This is the basic definition which we know. Now what you can do is, now I need to just convert it into the A transpose A. So just multiply A transpose on the both side, then you will get A transpose V is equal to A transpose lambda V. Then this combination I am looking at, and this is the multiplication of a matrix with a vector. So let's say this is going to be some U, and you are going to get the A transpose A. U is equal to, again look at it, this is a scalar, this is a matrix, so I can interchange their position. So I am going to get the lambda U. And this essentially shows that lambda U is the eigenpair of A transpose A. So now this particular simple result will tell me that gamma 1 is equal to gamma 2. So these two matrices are same. Regardless, I'm having the A transpose and A transpose A, and this is nothing but the singular values or SVs of A. So again, this is not exactly the SV values. We will see within a moment why. So this will lead to the singular values of the matrix A. This particular thing will lead to V. So Q is nothing but V, R is nothing but U. Then the singular value decomposition of A is nothing but going to be U, which is nothing but R. Then we are going to have this sigma 2. So this is going to be the square root of gamma. If I say this is going to be gamma 1 is equal to some gamma and V transpose. So can anyone explain me why this is going to be square root over here? And this is nothing but your singular value. After looking at this analysis, can anyone tell me? So these lambda are going to be the eigenvalues of A transpose A. Then how it will become the singular values of A? Can anyone tell me that? Just look at the given matrix. Anyone? What is the meaning of eigenvalue of A transpose A? So in this, the contribution of A is going to be twice. Double हो गया, दो बार हो गया. Since this is a multiplication, then that contribution is again going to be squared. And hence, in order to find out the singular values of matrix A, you have to take the square root. So let me give you very simple homework for you. You just think over it. Why the singular value sigma is going to be the square root of this matrix gamma, which we are going to get the eigenvalues of either A transpose or A transpose A. And if you are not able to identify this, the answer we will discuss in the tomorrow's lecture. So let me take this as a very simple example for. So hence the SVD which we are going to obtain for a particular matrix that has to include the path of this A transpose and A transpose A. So now we are going to have the enough ingredient which is going to define the algorithm for the singular value decomposition. The only thing which you need to understand is one matrix is n cross and other matrix is d cross d. In case of square, you can start with any of the matrix because you need to identify the eigenvalues and eigenvectors of this particular matrix or this particular matrix. You can do that. But however, in this particular case, when the matrix is rectangular, if n is greater than d, then the meaning is if you're trying to take this particular matrix, then you are going to have you have to do a lot of effort in order to find out n eigenvalues. However, if you take this matrix, it is going to have the same. You going to have the less effort in order to finding out the eigenvalue because the matrix the dimension is d by d. So can anyone tell me how is it possible? Here I am going to get the n eigenvalues and here I am going to get the d eigenvalues and I am saying n is greater than d. Then what will happen to n minus d? So the meaning is the first d components are non-zero and rest of the elements are going to be zero. And hence here this matrix is going to be singular symmetric matrix. But this matrix is not going to be singular if d is going to be less than n. If n is going to be less than n, then this is singular or this is not going to be singular. Because the validity of this relation will make the rest of the singular values as zero when after beyond the rank of this particular matrix or whatever the value is lesser is going to be there. And hence you are going to have the combination of the. So in order to find out non-zero eigenvalues of any of these particular matrix, you will always choose a matrix having the less dimension, and that is going to be the first step of the algorithm. So let me give you a very algorithm, not example. I think I am missing one slide. Yes, someone is saying something.
Yes, sir, I have.
Is there any issue?
Please go to the last slide.
Okay.
Sir, to show A transpose and A transpose A has the same eigenvalue, can we use the concept that A and A transpose has the same eigenvalues? Because of A
Yes,
transpose.
you can use. You can use. If that is applicable, certainly you can use.
Thank you, sir.
But that I think that result is not actually applicable here. Just look at it. But if it is applicable, you can use that. So I'm not getting into the discussion why it is not applicable. You just take the transpose of any of the matrix. You come to know what exactly you are doing. If it is applicable, then definitely you can use it. Otherwise, this is going to be the very simplest proof of the same. Okay, so the algorithm, the first step is going to be, the very first step for me is going to be construct either A transpose or A transpose A. So again, as I mentioned in the previous slide, whose dimension is less, just choose that so that you are going to have the less computation in order to find out the eigen values or the singular values of the matrix. So the first step says construct either A transpose or A transpose A, and then the second step is going to be find the eigenvalues and eigenvector, find eigenvalues and eigenvectors of the chosen matrix. If you chosen A transpose, then for A transpose, if you chosen A transpose A, then for that. Or A transpose A. The third is construct the singular value matrix sigma from the eigen vectors which you are going to receive from the previous step. So whatever eigenvectors you are going to get, eigenvalues you are going to get from this particular step, construct the sigma out of it. Fourth, construct u or v from the sorry, I did a mistake. So this is going to be the eigenvalues, and this is going to be the eigenvectors. So when you will get u, when you will get v, so it depends on when you are going to have the A transpose A or A transpose. Generally, A transpose will lead to v, and A transpose A will lead to u. So if you have chosen in the first step A transpose, then ultimately you will get the sigma and v, and if you have chosen A transpose A, you have essentially get the sigma and u. So as long as you are going to have this, the fifth step says use relation A is equal to u sigma v transpose to obtain the missing matrix. So if you have obtained u in the previous step, as soon as you will get the u, then A is known, u is known, sigma is known, then using this relation you can always find out the matrix. And if you have v over here, then A is known, sigma is known, v transpose is known. You can again use this particular relationship to get this particular matrix u. So this is the very simplest algorithm which you are going to have for finding out the SVD. The only issue with this algorithm is now you have to be very cautious when you try to find out the full SVD and when you try to find out the reduced SVD. But as I mentioned that we are more concerned about the reduced SVD, so I'm not going the extension of this algorithm for the full SVD. I'm just talking about the reduced SVD. So basically, this is the algorithm for finding the reduced SVD. So there is one more step 6 when you try to have the full SVD, but since there is going to be the little applicability of that particular scenario, so I'm not going into that. So let us stick to the reduced SVD. So whenever you are going to have the reduced SVD, then this is going to be the algorithm, and if you follow this particular path, then you are going to have the SVD of A matrix. So I think I have sufficient time to do one example. So let me try to do one example where we try to find out the SVD of a given matrix. So I think yes, I am going to have one blank slide with me. So let me take one example. So the example says find the SVD of or the reduced SVD of matrix A, which is nothing but 1, 2, 1, 2. So this matrix, is it visible that it is going to be a singular matrix, and we are looking for the SVD of this particular matrix to obtain. So as soon as A is given to you, you will immediately find out A transpose and A transpose A. So A transpose is again going to be a 2 by 2 matrix. A transpose A is again going to be 2 by 2 matrix because I am going to have a square matrix with me. So if I am going to have the rectangular matrix, then you are going to have the different dimension. So in this particular case, I can choose any one of it. So let me choose first step. Let me choose A transpose A. So the A transpose A is nothing but multiplication of these two matrices, and let me quickly write down the matrix 2, 4, 4, 8. So is it correct? Can anyone check it? If I do the A transpose A, should I get the same matrix with which I am getting over here?
Yes, sir, it's correct.
Yes, correct. Okay, thank you. Okay, so now this is my first step. It says that you have to find out A transpose A. What is the second step? Second step says you have to find out the eigenvalues and eigenvectors. So you can immediately find out the characteristic equation of it, and then you have to solve it to get the final thing. And I'm hoping that you are aware how to find out eigenvalues and eigenvectors. So let me give you the values directly to you. So since this is going to be 2 by 2 matrix, so then they are going to be the 2 eigenvalues and corresponding to eigenvectors. So let me say lambda 1 is the first eigenvalue is going to be 0, and the corresponding eigenvector for this is going to be minus 2 by root 5 and 1 by root 5. So this is the first eigenvalue. Then I'm going to take the second eigenvalue. That is going to be lambda t is going to be 10, and the corresponding eigenvector is going to be 1 by root 5 and then 2 by root 5. So whenever you try to find out these eigenvectors, please make sure that you are going to take the normalized vector as the eigenvector. So now if you look, if you able to find out the length of this particular vector is going to be 1, and this is again going to be 1. So if you are getting a eigenvector with respect to any of the eigenvalues which are not normalized, please normalize it. Maybe we can write that thing over here that we have to find out the eigenvalues and the normalized eigenvector. So we have to find out all the eigenvalues and the corresponding normalized eigenvector. If in the process you are getting normalized eigenvector, it's okay. If you are not getting the normalized eigenvector, please normalize it by dividing the length of those vectors to get the normalized eigenvectors. So these are the normalized eigenvectors which I have obtained with respect to lambda 1 is equal to 0 and lambda 2 is equal to 10. So as soon as you are going to have this second step done, so again, please verify this homework. So teacher is the person who always give homework to the students. That's the philosophy which we have in the elementary school. So now I am also giving the homework to you. So I hope that you will do this homework just for the better understanding of the singular value decomposition. Okay. Anyways, so what is the third step which we are going to have? The third step says that first we have to construct the singular values, and the singular values is nothing but the square root of these eigenvalues. So sigma is nothing but a 2 by 2 diagonal matrix where we are going to have the square root of these values. So this is going to be my sigma for this particular problem. So as long as I'm going to have this particular sigma, what you are going to have now? So you have taken the A transpose A. So A transpose A will lead to U. So the fourth step says the matrix U is nothing but the collection of the eigenvector with respect to eigenvalue. Since I have taken this root 10, the bigger one first, because I have to arrange these singular values in a decreasing fashion. So now the first vector I am going to take with respect to the bigger singular values, and that is going to be this particular vector. So I will get 1 by root 5, 2 by root 5. In the same, since the second singular value is going to be 0, so now the eigenvector with respect to the corresponding eigenvalue will come. So this is going to be minus 2 by root 5 and 1 by root 5. So this is going to be my U. So this is my fourth, and then a 5 step says that if as long as you are going to have sigma and either U or V, just exploit the relationship, which is nothing but A is equal to U sigma V transpose to get your what you say to get your the remaining matrix V. So now there are two ways now. Either you can use the matrix multiplication concept overhead and to get this final answer, or you can exploit the vector definition or vector representation of it, which is going to be quite easy because one vector is going to be with another vector. So that is going to be more straightforward and same. So what will happen over here in the vector representation? A can be written as can anyone tell me? Summation of sigma I, summation over I. Then what you have in the UI VI transpose. This is going to be there. If you go back and you are going to have the definition, I'm just talking about this vector representation. So vector representation is sigma UI VI transpose, and the summation will run over I. So using this, what is the ith relationship? Ith relationship says A is equal to sigma I UI VI transpose. Now in this, I have the value of A, I have the value of sigma I have the value of UI, and I'm going to have the value of this. I need to find out the value of VI transpose. So now how you are going to get that? Now you just plug in all the values and then try to do the same thing and you are going to get the final value. So how? So I can immediately say that VI transpose is equal to, so VI transpose is nothing but 1 over sigma A, UI transpose, UI multiply VI transpose is nothing but 1 over sigma A. So now you can plug in the value of UI and A over here and you are going to get the final values of V. If you feel that this is going to be tiresome or is going to be very, you can say, complicated, then just try to use this relation. A is given to you, A is 1, 2, 1, 2, and then U is again you have identified which is going to be this particular matrix. You can write down over here. Sigma is again, you know, do 10, 0, 0, 0, and then this is going to be, let's say V11, V12, V21, V22. So this is going to be, so now just construct a system of equations and then try to find out the values of V11, V12, V21 and V22 to get the final solution. So it is up to your, it is up to you which way to go. And again, you can follow the any of the path because I know that this is going to be the invertible matrix, this is going to be the invertible matrix. So the multiplication of two invertible matrices is again going to be the invertible matrix. So you can quickly multiply these two and then multiply by the inverse of this matrix on the both sides. Immediately you will get your V. So this way it is going to be quite easy to solve. But in some cases, this multiplication is going to be very tedious, especially when you are going to have the size of your matrix very large. Like let's say if I'm going to give you a matrix of 4 by 5, then the multiplication will take some time. But as long as you are going to 2 by 2 matrix, then this matrix definition will work. Otherwise, you have to follow this particular value. So let me give you the final value of V. I'm not going to give you the value. So, or you want to try? Okay, so let me give one more homework. Please give me the value of V, and then we are going to have one more example going to done in the next class. I think Dilmit, we have time or is over? I think the time is almost over, so I will stop there today, and then we will continue our discussion on the single value decomposition in the next lecture. That's tomorrow, and then we will start with the same problem, and I will ask you to give me the matrix V. So I hope that you are going to find out the matrix V after this simple multiplication and then taking the inverse of this particular matrix. Okay, so please give me this V in the next lecture, then we will discuss further, and then we will see the example of singular value decomposition in mathematics as well as in form of the principal component analysis. So thank you very much, and now I will welcome your questions or queries which you might have in today's lecture. So any query you might have? Okay, anyone? If you have any query, you can please either write in the chat box or maybe you can unmute yourself and we will have a discussion on that.
Sir, in between you have asked one question. Could you repeat that question related to singular value decomposition? A is equals to U summation V transpose. You were asking something related to under root thing. So
okay, I am saying that when you find out the eigenvalues of A transpose, then the singular values are nothing but the square root of those eigenvalues of A transpose or A transpose A. So why this square root is going to be there?
okay.
That was my question.
Okay, sir.
So I always in this example only when I try to construct the singular value matrix, what I did is I took the square root of the eigenvalues of A transpose A. So why this square root I need to take? So
Okay,
you
so
just need to understand that.
So sir, I'm working on that only. So we have A is equals to U summation V transpose.
Yeah.
So if we do A dot A transpose, so it will be U summation V transpose dot V
Yes.
summation transpose U transpose.
Yeah, exactly.
So it will boils down to U summation transpose U
I think you have
transpose.
given the you have given the solution to all. Okay, if you have given the solution, then quickly let me also give. But I want definitely I'm going to want that you are absolutely right. Whatever you said is absolutely correct. So let me quickly give that solution to all on this particular point of slide so that I think one of your solution is going to be actually done now. So okay, so the solution of this is why it is going to be the square root is I know that A is equal to U sigma V transpose. Okay, then you have to what you have to do you have to multiply with A transpose. So first I need to identify the A transpose over here. So what is the A transpose? Is nothing but U sigma V transpose whole transpose, and I know that A B whole transpose is nothing but B transpose A transpose. So if I use this formula, what I will get? I will get V transpose transpose, that is going to be V. Then sigma transpose is going to be just sigma, and E is going to be U transpose. So now try to take the A transpose A is nothing but V sigma U transpose and then U sigma V transpose. What you will get? You will get V sigma square, because this is the orthogonal matrix, then you are going to get I, and it's going to be V transpose. So the eigenvalue, because the eigen decomposition which we got is like Q transpose. So A transpose A will give you V, as well as the sigma square is nothing but this. So the sigma is nothing but the square root of sigma, and this is going to be diagonal matrix. So essentially this will boils down to the sigma is equal to square root of lambda. So this is nothing but the very simple proof of the thing why singular value is always going to be the square root of the eigenvalues of either A transpose A or A transpose. So I appreciate, by the way, who was the one who was telling me the solution? What is your name? I think Shivani.
Yes, sir, Shivani Chauhan.
Yeah, so I really appreciate that you have captured the motivation which will lead to the singular value decomposition in a very correct manner. So I appreciate
Sir,
it.
in your solution, you have assumed that summation means we should write summation transpose, because that summation matrix need not be a square matrix. It could be a
No, but it
rectangular
is going to
matrix.
be rectangular diagonal matrix. So of course that
Yes.
zero is not going to create any problem. So
Okay.
without loss of generality, if I don't have a well-defined value of this sigma, then I can always say that it's going to be the simple, as we are going to do what the diagonal matrix, we can do it for this as well.
Okay. And I
Because
understand,
this
sir.
is going to be a sparse matrix. Most of
Right.
the elements are going to be zero.
Yes.
So it's not going to make any sense.
Okay, sir. Okay. Thank you, sir.
Okay, no issues. So any other query? Okay, so I think if there are no further queries, so I will stop here today. And in the next class, we will see a few applications of SVD, and then we will lead to the ultimate goal of finding the principal component analysis and how the principal component analysis will work. We will see in the next lecture. So
Thank
this
you,
will
Gaurav.
be, yeah, okay, thank you.
Thank you, Gauravji. Thank you for this lecture. So tomorrow we have two lectures, 1 hour each. One will start at 5 p.m. and other will at 6:15 p.m. Okay. So thank
Sure.
you. Bye. Good night.
Yeah, good night, everyone. Bye.